There is a question that most people stop asking around the age of 7, not because they find the answer, but because the adults around them get uncomfortable and change the subject. The question is this: what comes after infinity? A child asks it and means it genuinely. If infinity is the biggest number, what is bigger than the biggest number? And the adult smiles and says, nothing is bigger than infinity. That is what infinity means. And the child accepts this, and the question goes away. But it never fully disappears, because the child sensed something true before the answer arrived to close the door. The question was not naive. The question was exactly right. And a German mathematician named Georg Cantor spent his entire life proving it. My name is Emmy Noether. I worked in abstract algebra and mathematical physics, and I spent most of my career in a world that was reluctant to take my ideas seriously. I know what it means to see something clearly that the people around you refuse to look at. And I know what the prolonged weight of that refusal does to a person. Georg Cantor knew it too, more completely and more devastatingly than almost anyone in the history of mathematics. This is his story. And it begins, as so many stories about genius begin, with a child who could not stop asking questions. Cantor was born in St. Petersburg in 1845, the son of a Danish merchant who had settled in Russia. His father was a man of deep religious conviction, who communicated that conviction not as a set of rules, but as a way of seeing, the belief that the world had a structure beneath its surface, a pattern beneath its apparent chaos, and that finding that pattern was itself a kind of devotion. His mother came from a family of musicians. Cantor himself had genuine musical ability as a young man. He played the violin. He understood, early and intuitively, that mathematics and music shared something essential. Both were languages for describing relationships that could not be expressed any other way. The family moved to Germany when Cantor was 11, after his father's health declined in the northern climate. They settled in Frankfurt, and then Cantor was sent to schools in Darmstadt and Wiesbaden. He was, by every account, a quiet and intensely focused student, not difficult, not disruptive, simply somewhere else, in a way his teachers noticed but could not quite name. He was present in the classroom and absent from it simultaneously. His body sat at the desk. His mind was in a place the curriculum had not yet mapped. By the time he reached university, studying first in Zurich and then in Berlin, the question that would consume his life was already forming. It was not a question that most mathematicians of his era thought was worth asking. It was, in fact, a question most believed had been definitively closed. The question was about infinity, about what it was, about whether it was one thing or many things, about whether it could be measured, compared, understood with the same rigor mathematicians applied to numbers they could write on a page. The prevailing view was that infinity was a limit, a concept, not a quantity. You could approach infinity the way you approach the horizon, but you could never arrive there, and you certainly could not do arithmetic with it. The great mathematician Carl Friedrich Gauss had expressed this with characteristic authority. He wrote that he protested against the use of infinite magnitude as something completed, which in mathematics was never permissible. Infinity was a direction, not a destination, a way of speaking, not a thing that existed. Cantor looked at this position and saw something others had missed. He saw that it assumed its own conclusion. It said infinity could not be a completed quantity, therefore we will not treat it as one, therefore we will not discover whether it can be. The circle was closed before the question was asked, and Cantor, who had inherited from his father a conviction that the deepest truths had a structure, was not willing to close that circle. He began working on infinite sets in the early 1870s, in his late 20s, as a professor at the University of Halle. The work started modestly, a technical question about whether a function could be represented by a trigonometric series in more than one way. The answer required him to think carefully about infinite collections of points on a line, and that thinking led him somewhere no one had been. He began to ask, are all infinite sets the same size? At first glance, the answer seems obvious. Infinite means infinite. It means going on forever. How could one thing that goes on forever be larger than another thing that also goes on forever? But Cantor noticed something. He could construct a precise method for comparing the sizes of infinite sets, not by counting them, since neither could be counted, but by asking whether the elements of one set could be matched one-to-one with the elements of another. If every element in set A could be paired with exactly one element in set B, with none left over on either side, then the sets were the same size. This was not a new idea, but Cantor followed it further than anyone before him. He asked, can the counting numbers 1, 2, 3, 4, going on forever, be matched one-to-one with the even numbers 2, 4, 6, 8, also going on forever? The intuitive answer is no, because the even numbers are a subset of the counting numbers, and a part cannot equal the whole. But Cantor showed that they could be matched perfectly. Every counting number n pairs with the even number 2n. 1 pairs with 2, 2 pairs with 4, 3 pairs with 6. The matching never fails. The sets are, in his precise technical sense, the same size. This was strange. It violated the intuitive principle that the whole is always greater than its parts. But the mathematics was impeccable. He extended this further. The rational numbers, all fractions, all numbers that can be written as ratios of whole numbers, seemed vastly more numerous than the counting numbers. Between any two whole numbers, there are infinitely many fractions. Between 1 and 2 alone, fractions like 3/2, 5/3, 7/4, and infinitely many more. Surely the rationals were a larger infinity. Cantor proved they were not. He constructed an elegant method, a diagonal path through an infinite grid of fractions that matched every rational number with a counting number without missing any. The rationals, despite their apparent density, were the same size as the counting numbers. He called sets of this size countably infinite, and then he asked the question that changed everything. What about the real numbers? All the numbers on a continuous line, not just fractions, but irrational numbers like the square root of 2, and transcendental numbers like pi, which cannot be expressed as fractions at all. Could the real numbers be matched one-to-one with the counting numbers? His proof that they could not is one of the most beautiful arguments in the history of mathematics. It is called the diagonal argument. He showed that if you claimed to have a complete list of all real numbers between 0 and 1, matched one-to-one with the counting numbers, he could always construct a real number that was not on your list. no matter how cleverly the list was made. He looked at the first digit of the first number and chose a different digit for the first position of his new number. Then the second digit of the second number on the list and chose differently. Then the third digit of the third number. By construction, his new number differed from every entry on the list in at least one position. It was a real number between 0 and 1 that the supposedly complete list had missed. Therefore, no such complete list could ever exist. Therefore, the real numbers could not be matched with the counting numbers. Therefore, the real numbers were a strictly larger infinity. There are different sizes of infinity, not a metaphor, not a philosophical position, a mathematical theorem proved with the same logical rigor as any result in Euclidean geometry. The counting numbers and the real numbers are both infinite, but they are not the same size. The real numbers are larger. And Cantor did not stop there. He proved that from any infinity, you could always construct a strictly larger one, that the infinities themselves formed an infinite ascending hierarchy with no ceiling, no final largest infinite set. He called these the transfinite numbers. He developed arithmetic for them. He spent years building the theoretical foundations of what he called set theory, the study of collections of objects, which would eventually become the foundational language of all of modern mathematics. The response from the mathematical community was not admiration. It was, in many cases, something closer to fury. The most sustained and damaging opposition came from Leopold Kronecker, one of the most powerful figures in German mathematics. Kronecker had a philosophical conviction, not just a professional disagreement, that only finite, constructible mathematics was legitimate. God made the integers, he famously declared, all else is the work of man. He did not merely disagree with Cantor's conclusions, he found the entire enterprise offensive. He called Cantor a corrupter of youth. He described the work as a mathematical disease. He used his considerable influence to block Cantor's appointments, to prevent him from ever securing a position at Berlin, the most prestigious university in Germany, where Cantor had studied and where he had hoped to build his career. Cantor spent his entire professional life at Halle, a provincial university he had never intended to stay at, in a position well beneath what his work deserved. This was not an accident. It was the result of a sustained campaign by a powerful man who found his ideas threatening to the mathematical order he had built his authority upon. What made this especially bitter was the contrast between how Cantor's ideas were received at home and how they were beginning to be received elsewhere. Mathematicians in other countries, in France, in Sweden, in Italy, were reading his work with growing fascination. The Swedish mathematician Gösta Mittag Leffler, who edited one of the leading mathematical journals in Europe, corresponded with Cantor regularly and published his work. Henri Poincaré, the greatest French mathematician of his generation, engaged seriously with the transfinite numbers, even as he had reservations. The isolation was specifically German, specifically institutional, specifically the product of one powerful man's opposition, and Cantor knew it. He could trace the line from Kronecker's influence to every closed door. He was not imagining the obstruction. He was living inside it. The professional damage was real. But what the campaign did to Cantor internally was something harder to measure and more lasting. He was not a person who could simply detach from the reception of his work. He wrote long, careful letters to mathematicians across Europe, explaining his results, addressing objections, demonstrating his rigor. He sought engagement with an intensity that, in a different environment, would simply have been the normal hunger of a serious intellectual for serious conversation. In the environment he actually inhabited, it became something more desperate. He needed to be understood. He was not being understood, and that gap, sustained for years, began to do what sustained impossible gaps do to human beings. There was also a different kind of exhaustion building, one that had nothing to do with professional opposition. Cantor was a deeply religious man, and his transfinite mathematics had for him a theological dimension that he was never entirely able to separate from the technical work. He believed that the infinite hierarchy of infinities he had discovered pointed toward the absolute infinite, toward God in the language his father had given him. He wrote theological letters alongside his mathematical ones. He corresponded with Catholic theologians who were trying to understand whether his mathematics was compatible with church doctrine. He wanted the two worlds, the mathematical and the spiritual, to confirm each other. When the mathematics became uncertain, when the continuum hypothesis refused to yield, it was not just an intellectual problem. It touched something closer to the center of how he understood his own existence. The first severe breakdown came in 1884. Cantor was 39. He had been working at ferocious intensity for over a decade. He was deep in an attempt to prove what he called the continuum hypothesis, the question of whether there existed an infinity between the countable numbers and the real numbers, or whether the reals were the next infinity up with nothing between. He could not prove it. He could not disprove it. He would construct what seemed like a proof, examine it carefully, and find the flaw. He would try the opposite direction and find a different flaw. The problem resisted every approach. He collapsed. He spent months in a sanatorium. His letters from this period are difficult to read. A man who had seen further than almost anyone in his field, writing from inside a fog where the light he had been following had gone out, and he could not locate it again. He recovered. He returned to work. He continued publishing. And in the intervals between the darkest periods, he produced some of his most carefully reasoned writing, not just mathematics, but philosophical and theological essays defending the legitimacy of the actual infinite, arguing against the philosophers and theologians who found his work dangerous, trying to build a complete picture of why the transfinite numbers were not an assault on the order of things, but a revelation of it. He was working on too many fronts simultaneously: the mathematics, the philosophy, the theology, the career, the illness. Each one demanded something from him that the others had already used. But the breakdowns came again. In 1899, in 1902, in 1904, in 1907, in 1911. Each interval produced more mathematics. Each collapse went deeper. In the gaps between hospitalizations, the person who wrote careful papers on transfinite numbers was also a person who asked God, in letters to his wife that are almost unbearable to read, why the vision had been given to him, if the vision was also the instrument of his destruction. I do not think there is a clean answer to the question his biographers keep returning to, whether the mathematics caused the illness or whether the same quality of mind that allowed him to see what others could not also made him more vulnerable to a particular kind of anguish. I think both are true and cannot be separated. The thing that let him see the structure of infinity was the same thing that could not set the work aside when it became painful, could not distance itself from the rejection, could not survive the particular loneliness of being right in a room that insisted you were wrong. By the early 1900s, set theory had spread through the mathematical world with a speed that reflected how much it was needed. Mathematicians working on the foundations of analysis, on topology, on logic, on the theory of functions, all of them found that Cantor's language gave them tools they had not had before. The ability to speak precisely about infinite collections, to compare their sizes, to build arguments about limiting processes and continuous functions, these depended on the framework Cantor had constructed. What had seemed like a dangerous speculation was turning out to be a load-bearing wall. David Hilbert, who would become the greatest mathematician of the early 20th century, declared that Cantor's paradise, his phrase for the world of transfinite numbers, was a paradise from which no one would expel us. He called Cantor's work one of the supreme achievements of purely intellectual human activity. A new generation was building the foundations of mathematics in the language Cantor had created. Set theory became the bedrock on which modern mathematics stood. But this recognition came too late for Cantor to fully receive it. He died in January 1918 in a sanatorium in Halle, where he had spent his final year writing letters to his wife asking to come home. He was 72 years old. Outside, the First World War was in its final year. The Europe that had formed him, the Europe of letters between mathematicians, of congresses in Paris and Rome, where ideas crossed borders freely, of journals that carried theorems from Halle to Stockholm to Cambridge, was being destroyed by the same industrial civilization whose physical infrastructure rested invisibly on the mathematics he had built. He did not know this. He was in a room writing to his wife. He wanted to come home. There is a final detail in his story that I cannot pass over. The continuum hypothesis, the problem that had broken him in 1884, the question he could neither prove nor disprove across 30 years of trying, was eventually shown to be undecidable. Kurt Gödel proved in 1940 that it cannot be disproved within standard mathematics. Paul Cohen proved in 1963 that it cannot be proved either. It is, in the formal language of mathematical logic, independent of the axioms of set theory. It lives in a space where the tools of formal proof cannot reach. Cantor spent decades in anguish over his inability to resolve it. The reason he could not resolve it was not that he was missing something. It was that the question was genuinely, mathematically, provably beyond resolution from within the system. He was not failing at a solvable problem. He was encountering a fundamental limit of formal thought, a limit that would not be understood until decades after his death. He was not wrong. He was early. And the distance between those two things is sometimes measured not in years, but in a human life, spent mostly in rooms with locked doors. The child who asks what comes after infinity is asking a real question. Cantor answered it. There is not one thing after infinity. There is an infinite hierarchy of infinities, each strictly larger than the last, ascending without end into a structure that has no ceiling and no final resting place. He gave us this. He built the language we use to say it. He proved it with the kind of rigor that does not bend under examination, no matter how many times you look. And it cost him everything he had. The question was always right. The question was always exactly right. He proved it. He gave us the language. He paid the price. Sometimes that is the most expensive thing a question can be.